Dobry wieczór Państwu. Witam Państwa na wykładzie profesora Kipa Thorne'a z okazji 100. i 110. rocznicy publikacji jednych z najważniejszych artykułów, których ukształtowały nowożytną fizykę. Nazywam się Marcin Zarut, jestem specjalistą w dziale wystaw i komunikacji naukowej i żeby uhonorować naszego gościa, dalszą część zaproszenia już powiem po angielsku. Ladies and gentlemen, I wish to welcome you at this evening on the lecture about theories of relativity. My name is Marcin Zarut. I'm a science communicator at the Science Communication Department here at the Copernicus Science Center. And I'm very honored to welcome Professor Kip Thorne, today's evening speaker. This honor comes from two sources. First of all, Professor Kip Thorne is one of the best-known theoretical physicists of our age. And second, Professor Kip Thorne is also a very gifted science communicator. In both of these roles, he's a personal role model for me and many of my colleagues here at Copernicus Science Center. But today is a lucky day for me because here at this audience, I have not one role model and very inspirational figure, but two of them. Second of them is Professor Łukasz Turski, our chief of our scientific council, founder and idea gifter of the Copernicus Science Center. And he's also very inspirational for me and my colleagues working here in Copernicus Science Center. So Professor Łukasz Turski is a founded idea of this lecture and made it possible to happen. So please welcome him.
Good evening, ladies and gentlemen. In the summer of 1913, two distinguished magicians of world science, Walter Nernst and Max Planck, were standing on the Limmat K platform of the Zurich funicular, waiting for an individual to come down the hill. And what they were looking for were not tablets in the hands of this individual, but the color of the flower he was holding. Albert Einstein promised that the flower will be red if he will accept the offer to go to Berlin. As the history tells us, the color was red. And 2 years later, exactly 100 years and 1 day ago, Albert Einstein completed his presentation to the Prussian Academy of Science of the most powerful and beautiful theory ever invented by the human mind. The theory which we now call a general theory of relativity. It is a great pleasure for all of us to have on that occasion of this jubilee of general theory of relativity with us this evening Professor Kip Thorne from Caltech. As it was already said, he is one of the contributors to the general relativity, cosmology, astrophysics, and he's also a science communicator. He also was able somehow to inspire artists to show this beautiful and also a cruel universe of ours in the movie called Interstellar. So as one of the heroes of the Interstellar says, that's relativity, folks. Professor Kip Thorne, the floor is yours.
Thank you very much, Professor Turski. Can you hear me in the back? back. Okay, can we adjust the microphone? Can you hear me now? No? I thought I turned it on, but I'm fairly incompetent. Can you hear me now? Okay, it's obviously my incompetence. Excuse me. It's a great honor and pleasure to be here at the Copernicus Science Center. I'm so impressed by it. I was taken as a walk tour through it for a little while before this lecture by the director, and it was such an impressive thing. I've been to the Exploratorium in San Francisco. This is at least comparable, if not better. Congratulations. I really congratulate you on this. I'm going to begin my lecture by talking about the movie Interstellar as a preamble, because I will use a few scenes from Interstellar to illustrate the ideas of general relativity theory. Let me begin by telling you that the very genesis of this movie was a failed romance. I was introduced to a young woman named Linda Obst by Carl Sagan, an astrophysicist friend of mine. He called me one day, this is a long time ago, in 1979, and he said, "Can I set you up on a blind date with a friend of mine who has just moved to Los Angeles, and she would like to meet you?" And so it was Linda Obst. We went out, the romance failed, but a close friendship ensued. She's a close friend of me and my wife, whom I married later. Some years later, in 2005, Linda telephoned me and said, "Would you like to brainstorm with me for ideas for a new science fiction movie?" And I thought about this for a few milliseconds, and I said yes. Because I realized that this could be an opportunity to reach a much broader audience in science communication than I had ever been able to reach in any other way. And in fact, I have. Through the movie Interstellar, I've reached approximately 100 million people around the world, which is impressive for a physicist, very impressive, and really quite amazing. And so Linda and I brainstormed for a movie whose name we invented as being Interstellar. And the idea was to have a movie in which general relativity is embedded into the very fabric of the movie from the outset. That the venue, the surroundings, the environment for the movie would be what things that are predicted by Einstein's general theory of relativity. And so then, after we had written a treatment, which is a description of all the science that underlies the movie, it appears in the movie in our case, plus the characters in a short version of the story, Linda brought on Jonathan Nolan to write the screenplay. Now, this is a short version of the story. She actually brought on Steven Spielberg to direct it initially. Steven dropped out a little bit later after having had some significant influence, particularly on me. But in the end, the movie turned out to be the Nolan's movie and not Spielberg's. So anyway, she and then Steven Spielberg brought on Jonathan Nolan. Jonathan was a young man who had only written screenplays for 3 movies previously, for his brother's movies, Christopher Nolan's movies, Memento, The Prestige, Batman, The Dark Knight. And so Jonathan, or Jonah, and I brainstormed through 3 drafts of the screenplay, meeting together at the Caltech Faculty Club, where Caltech is the university where I work, for several hours every other week or so over a long period of time, just discussing the science ideas for the movie as he developed the screenplay. And he changed half of our original story. And then Linda brought on as the director, after Steven Spielberg dropped out, Christopher Nolan, Jonah's brother. And Chris and I brainstormed together for about 6 months over 3 more drafts of the screenplay. Chris always writes the final drafts of his screenplays, or whoever writes the earlier screenplays, so that he will know precisely what the form of each scene is, and it's so designed that he knows precisely how he's going to shoot it or implement it through visual effects. So we had a great collaboration, and I'm going to talk a little bit about these collaborations later when I get into some of the meat of this lecture. We had a wonderful collaboration developing the screenplay. And the final screenplay, he changed the other half of the story. So the story is entirely the Nolan's story, but the science vision of Linda and mine of general relativity built into the fabric is preserved, and that was really why the Nolan brothers wanted to work on the movie, and why Spielberg earlier wanted to work on the movie, to have the opportunity to work with a scientist on a movie in which the real science is the motivator, and which preserves the real science in the following sense, that we had made an agreement that nothing in the movie would violate well-established physical laws or well-established, well-understood aspects of the universe. And any speculations that were in the movie about science would always be speculations that come from real science or not just invented by the Nolan's minds. And Christopher Nolan, when I asked him would he accept this, he said, yes, of course, to the extent it does not get in the way of making a great movie. And the next sentence out of his mouth was, and if you don't like what I do with the science, then you don't have to defend me in public. But in fact, I do like what he did with the science, and so I am very happy to defend him in public. I felt it turned into a really great movie. There were compromises made in order to make a great movie, and I will tell you the most extreme compromise with the science when we go in here, which is related to the story of general relativity. But let me move on. So this was the Nolan's movie, not ours. So that is the end of the preamble. Now the prologue, going back to general relativity theory, Einstein's audacity. And this is what led up to Einstein's general theory of relativity. So I want to talk about Newton and Einstein. Newton in 1687 gave us a framework for the laws of nature that lasted for 218 years. A framework based on the concepts of absolute space and absolute time, forces, accelerations, the things of everyday experience. Einstein came along in 1905, 218 years later, and gave us a new framework called special relativity. And that framework is based on the principle of relativity, which says that all the laws of nature must be the same in every freely moving laboratory everywhere in the universe. And if you look at that and think about it for a moment, you realize that, in fact, is a law that governs all the laws of physics. And this took real audacity, real courage to claim that here is a law that governs all the past laws of physics that anybody has ever found and governs all future laws that anybody has ever, that will turn out to be successful. And indeed, the laws of the strong nuclear force, the weak nuclear force that came along after this, they all respect the special theory of relativity, Einstein's principle of relativity. This is truly a successful law that governs the laws of physics. So let me tell you now a weird consequence of this. If I go in and I measure the speed of light by looking at a photon, a particle of light that is moving past me, and I measure that speed of that photon to be 300,000 kilometers per second approximately. And if you then, in your sports car, are moving past me at a speed of 200,000 kilometers per second, you have a very fast sports car, then obviously the speed you must see that photon moving at is 300,000 minus 200,000, or 100,000 kilometers per second. Obviously, but it's not. Einstein's principle of relativity, when you look at it deeply, it says it cannot be that the speed of that photon has to be the same as measured by you in your sports car as it was as measured by me. And that seems utterly impossible. And when you look deeply, when Einstein looked deeply at why this can be, how it can possibly be, the answer is that you and I, moving at different speeds, we disagree about the distance that the photon traveled. We disagree about how long it took for the photon to make that trip. We disagree about which events in space and time are simultaneous. We disagree about all of these things. We do agree on the speed of light. But the reason that we can agree on the speed of light is that these other things are relative. They're different for you and me because we're moving at different speeds. And Einstein then worked out the details of how our measurements on length and time and simultaneity disagree, the precise details from his principle of relativity. So that was a great triumph. Einstein then went on and said, let me now look at Newton's laws of gravity. Newton tells us that the gravitational force that the sun exerts upon the earth varies as 1 over the square of the distance between the sun and the earth, where that distance is measured at moments that are simultaneous on the sun and the earth. That is, instantaneous moment of time between the sun and the earth. And Einstein said, yes, that's what Newton told us, but look here. The separation, d, is different as measured by the sun and the moon because they are moving at some speed relative to each other. And so which one am I supposed to put in, the distance between as measured by the sun or by the moon? And he said the concept of simultaneity or instantaneous is different as measured by the sun and the moon. And so that also presents a problem. He says the very foundational concepts that go into Newton's laws of gravity are wrong. They make no sense. They're incompatible with my principle of relativity. Therefore, he told us that Newton's laws of gravity violates my principle of relativity. Newton must be wrong. Now, that took some courage. Newton was the giant of all time in physics. Today, I look back and say, well, there were two giants, Einstein and Newton, and it's often debated who was the greater. I tend to think Einstein was the greater, but there are disagreements over this. But that they were the two giants of physics, there is no doubt. Einstein then said Newton must be wrong, and he had to create a whole new foundation for the laws of gravity. And the foundation that he chose, or that he found, is an extremely surprising foundation. It is so radically different from Newton's that it's really rather hard, unless you know deep inside these laws how he got there. It's very hard to see how he got here. He got there, and not now, let me say, I'm now moving on to a whole new description of gravity. I'm not yet to 1915. I'm now up to 1912. So this is Einstein's first step toward the new description of gravity. And it is what I like to call Einstein's law of time warps, though that's not what he called it. And what Einstein's law of time warps tells us is that things like to live where they will age the most slowly. And wouldn't you like to live where you will age the most slowly? And gravity pulls them there. And then Einstein gives us a formula that says that the gravitational pull is proportional to the amount of slowing of time. And a precise formula for this. So in the case of the Earth, then, what he says is that the Earth's mass warps time. It slows time on the surface of the Earth relative to at high altitude. And this warping of time is the thing that produces gravity. And that is really a radical departure. And so quantitatively, if you look at Einstein's formula for his law of time warps, what it actually says is that in order to produce the gravitational acceleration that we feel that holds us in our seats in this lecture hall, it is necessary that time be slower on the surface of the Earth than at high altitude, slower by 1 second in 100 years. Now that's not very much slowing of time, but that's the precise amount of slowing of time that's required to explain the Earth's gravitational pull. And this was verified to very high accuracy for the first time in 1976 when NASA flew an atomic clock to very high altitude and compared the ticking rate of that clock with atomic clocks back on the surface of the Earth. And to the precision of the experiment, 1 part in 10,000, or 1/100th of 1%, the formula that Einstein gave us was verified. So this really is true, this link between the slowing of time and the gravitational pull. Now, near a black hole, gravity is enormously stronger, so the slowing of time is enormously greater. And in the movie Interstellar, there's a black hole called Gargantua, a very big black hole. And in the movie, as Christopher Nolan conceived it, on Gargantua, 1 hour is the same as 7 years back on the surface of the Earth. That's an enormous amount of slowing of time. Why? Because the gravitational pull of Gargantua is so enormously strong at the location of this planet, which is near the surface of the black hole, near what we call its event horizon. And this plays out in the movie in a form that the 100 million people who have seen this movie will remember probably the rest of their lives. It's a very, very poignant moment in the movie, a series of moments. Cooper, played by Matthew McConaughey, speaks with his 10-year-old daughter and tells her that I'm going out into the universe and I may go near a black hole. And if I go near a black hole, it may be that when I come back from being near the black hole, because time flows so slowly for me there, that you may be as old as I am now when I come back out. And he does go near a black hole, and when he comes back out, his daughter has grown up to become a 31-year-old brilliant theoretical physicist. That's one of the reasons I like this movie. You have these very, very beautiful and interesting movie actors and actresses who play theoretical physicists. And let me just remark that Jessica Chastain, who plays the theoretical physicist, on the red carpet at the world premiere in Los Angeles, she talked about one thing, the joy of playing a theoretical physicist and working with me on the equations that she had to work with on the blackboard in this movie. And this was, in fact, a joy in this movie that everybody who worked on it was so enthusiastic about being tied to Einstein's relativity theory, being tied to physics in this way that they had never experienced before and will probably never experience again. So Cooper goes near the black hole one more time, and when he comes out, his daughter is now 90 years old, and he meets her by her bedside, surrounded by her children, her grandchildren, her great-grandchildren. And this is the really poignant moment, both sad and sweet, that Cooper sees his daughter near death, but having triumphed by saving the human race using information that he has fed to her. But the bottom line for me this evening is that here you see Einstein's law of time warps in real action in a way that 100 million people will probably never forget. Now, in 1912, Einstein realized that if time is warped, then space must also be warped. And this was first tested experimentally, again to very high precision, also in 1976, when NASA had placed the Viking spacecraft in orbit around Mercury. And Mercury carried then the Viking spacecraft on the opposite side of the sun so that radio signals sent out from Earth to the spacecraft and back, one after another, passed close to the sun. And then what Robert Riesenberg and Erwin Shapiro, who led this experiment, this was Erwin Shapiro's idea, did, was they said, if space is flat between the Earth and Mercury, the Earth and Mars, where the Viking spacecraft is, if space is flat between the Earth and Mars, where the Viking spacecraft is, then the round-trip travel time will be a certain amount. And the round-trip travel time was longer, and they made a plot of how much longer as a function of the position of the Viking spacecraft. And it was longer by something that rose up to several hundred milliseconds or microseconds as it passed close to the sun and then dropped back down. And that longer path just meant that space had to be warped in the vicinity of the sun as the radio tracking signal went near the sun. And so from that longer travel time, they were able to compute the shape of space around the sun. And to visualize that shape of space, what we can do is take that plane, I'll call it a plane in quotes, along which these radio signals traveled, and embed it in a higher dimensional flat space in which it will have to bend down so we can see the warping of space in the bending down in this higher dimensional flat space. This higher dimensional flat space is sometimes called an embedding space, but I like to use a word borrowed from theoretical physicists in string theory. Higher dimensional space is called the bulk. And in the movie, there are this higher dimensional space is a real space that really does exist. It's called the bulk in the movie, and there is a civilization of very advanced beings called bulk beings, or they, usually called they in the movie, and then at one point they're called the bulk beings that live in the bulk. They look in from the bulk and they can see the warping of space around the sun. And this is the shape of the warping of space around the sun. And in 1976, we had Einstein's full theory, and so you could compare this with the predictions of Einstein's full theory, and it agreed again to a precision of about a part in 10,000. So a beautiful confirmation of Einstein's full theory. But in 1912, Einstein did not yet have the full theory, but he understood warping of space. To some extent, he understood warping of time. And then he struggled to build an equation that is a law. The laws of physics, the language of the laws of physics are mathematics. And so a law is a mathematical equation. He struggled to find the law or the equation that governs the warping of space and time. And he struggled for 3 years in what he called the greatest struggle of his life. And finally, the triumph came 1 year and 1 day ago when he presented in written form his general theory of relativity to the Prussian Academy of Sciences. And as Marek Demiansky told me this morning, he presented a lecture on it 1 year ago today. So today is also the centenary of Einstein's general theory of relativity, his first lecture about the subject at the Prussian Academy of Sciences. And what he presented was an equation that describes how space and time are warped by the mass and the energy that live in space-time. This is Einstein's field equation. Those are the symbols that embody it. But in order to understand those symbols, you have to go deep into the mathematics that underlies it, which requires several years of study of mathematics to get there. But once you have studied the mathematics, you come away, everybody I know who has studied it comes away and says, this is really the most beautiful theory that the human mind has ever discovered, this general theory of relativity and the way in which this works. And this equation also tells us how the warping controls the motion of stars and spacecraft and light and everything else through the universe. Just a magnificent single equation with lots of underlying mathematics that is required to understand and work with this equation. The rest of my lecture is going to be about a few things that Einstein's equation has taught to us in this past century. And I'm going to first give you a list of these things. I'm not going to read the entire list, but just to impress you that there's a lot here, and that there are a number of buzzwords that many of you will have heard that will be in this list. And when you see this list and all of these familiar buzzwords like dark mass and dark energy and so forth, you realize there's no way I'm going to cover all of this in a lecture this evening. I need 7 hours at least in order to talk about all these topics. And I'm told I cannot have 7 hours. And so I'm going to then choose a very small segment of these. But in the brief in this past century, and I should also tell you the following. 50 years ago, when I was thinking that I would make my career working in this field, I spoke with a very famous astronomer who was my mentor when I was an undergraduate at Caltech. And I told him I really wanted to work in relativity theory, and he said, Kip, I don't think that's wise, because I think relativity theory, well, yeah, it is related to the expansion of the universe, but that's the only thing it's related to, and it's not going to be worth much otherwise, and this is going to be a desert. And he was completely wrong, but that was the common view 50 years ago, and it was just shortly after that that quasars were discovered, then pulsars were discovered, the cosmic microwave background left over from the Big Bang was discovered, and suddenly this whole subject opened up is turning out to be absolutely crucial for huge numbers of things, the things that I'm going to talk about, list briefly. There are high precision experimental tests of this have come about in the second half century. In cosmology, the Big Bang, inflation, and all of these buzzwords that will be familiar to many of you. Relativistic astrophysical objects, black holes, and then there's another long list here that isn't even complete in what I've given you. Geometrodynamics, something I will talk about a bit, the nonlinear dynamics of curved space-time. Again, buzzwords, but something very, very deep happened in our understanding of warped space-time. Gravitational waves opening a radical new window onto the universe, which I will say a little bit about. The incompatibility of general relativity with the other great set of physical laws from the 20th century, the laws of quantum theory, and the challenge of creating a new set of laws called the laws of quantum gravity, which synthesize these two sets of laws, and these being so crucial for understanding the birth of the universe and much else. I'll say a few words about that. Speculations, many of which appear in the movie Interstellar, such as wormholes and backward time travel, that I will not talk about unless you want to ask me about them in the questions. I want to focus primarily on things that are firm things that happen, rather than on things where we don't know yet for sure whether they're part of our real universe. So I will avoid those speculations unless you ask about it. And also, I want to tell you just a bit that through my career until the last decade, basically, I didn't have enough respect for the mathematicians. I had the attitude that we physicists are really doing the work to understand Einstein's relativity, and the mathematicians come in and they clean things up afterwards. But then it turned out that I was wrong in the sense that we were unable to solve Einstein's equations on supercomputers. Numerical relativity failed. Our computer programs crashed year after year after year. And it turned out to be because we did not understand the mathematical underpinnings and structure of Einstein's equations very well. And we had to go to the pure mathematicians and applied mathematicians to sort that out. And so really, mathematics has played a huge role in enabling us to do what it's doing. And it's doing so, again, in the area of string theory. So it's not just the physics, it's also the mathematics, and so forth. But I'm going to make an idiosyncratic, my own choice of topics to focus on today instead of going through this long list. And I'm going to focus on what to me are the most interesting things. They are things that don't involve matter. They just involve pure curved space-time or warped space-time. And I use curved and warped to mean the same thing. They have different connotations to an American mind. I don't know whether they do to you or not. And to me, the phrase warped is closer to the truth than curved, but curved is what physicists, the word physicists use. But anyway, I'll focus on pure curved or warped space-time without any matter present. So let me begin by talking about black holes. These are sort of the ultimate quintessential objects that involve pure warped space-time. A black hole is made from warped space-time. And it's not made from matter. You might object, you've been told that black holes are formed when a star collapses. After it exhausts its nuclear fuel, it collapses, gets smaller and smaller, and forms a black hole. That's true. But after the black hole is formed, the matter is gone. It has been destroyed in a singularity, we call it, inside the black hole, and there's none left. And the thing that is left behind is made purely from warped space-time. In some sense, sort of like the surface of a whirlpool without the water. It is a gravitational soliton. It's an object whose curvature or warping is created by the energy of the warping. It's like the snake that eats its own tail. The warping is produced by the energy that's in the warping, and the energy that's in the warping is the precise amount of energy that's required to create the warping, and it's a very stable object that holds itself together. And the shape of space for the black hole, as seen looking in from the bulk, is what I show here if the black hole is not spinning. Earth is way back far away where this becomes flat. This is just down near the surface of the black hole, the horizon. The color coding shows the slowing of time. So at this yellow point, time is flowing at 10% of the rate that it does back on Earth, and the yellow point being down here. And at the black point down here at the bottom, time has slowed to a halt. And so gravity is infinitely strong, and that's why nothing can get out from there. Infinitely strong according to Einstein's law of time warps. That's why nothing can get out. That's the event horizon. Now, the event horizon then looks like a circle here, but remember, I'm only showing 2 of the 3 dimensions of our space. In order to visualize things, I had to take only a 2-dimensional surface in our space and show what it looks like as seen from the bulk, because I'm not very good at drawing 3 dimensions living in a 4-dimensional bulk. So we call this our membrane, or our brain. It's 2 of our 3 dimensions as seen from the bulk. And if I restore the 3rd dimension, then this circle becomes a sphere, and the black hole's surface then is a sphere. Now, it turns out if the black hole is not spinning, the closest that Miller's planet can be to the black hole is up here. If it's any closer, its orbit is unstable, and the planet will fall into the black hole. And way up here, time is flowing almost the same as back on Earth. 1 hour at this location is 90 minutes back on Earth. And so when Christopher Nolan first told me that he wanted 1 hour on Miller's planet to be 7 years on Earth, I said, no, that's not possible. I'm quite sure it's not possible. It was based on this example of a non-spinning black hole. I knew that if a black hole was spinning, that it would be a little bit bigger amount of slowing, but I didn't think you could possibly ever get as much slowing as he wanted. Chris knew me by then, and he said, Kip, go do a real calculation and come back and tell me what it says. Because he had seen me be wrong several times before. And so I went and did a real calculation, and I came back very sheepishly, and I said, well, you have it. A very fast spinning black hole can be close enough to the horizon that time is slowed as much as you want for your movie. The key point is that as a black hole spins, it drags space into a whirling motion around itself like the air in a tornado. And the angular velocity of whirl is proportional to the length of these white arrows. So it's high near the horizon, it's low far from the horizon, just as the angular velocity of whirling air in a tornado is high near the core of the tornado and low far away from the tornado. And that whirl of space, it turns out, through centrifugal forces associated with it, it stabilizes the orbit and enables the planet to be so close that 1 hour in 7 years is possible. Now, I'll also tell you that when the movie first came out, and people didn't know that I had written a book about the science in the movie, a number of pundits, of scientists and science writers wrote blogs on the internet or in articles in newspapers saying, this movie is wrong. You can never have that much slowing of time. And when they read the book about the science of the movie, we were not allowed to advertise the book before the movie came out because Christopher Nolan was afraid that people who knew that there was a book about the science in the movie, they would get scared and they would not go to the movie. And he wasn't talking about this audience, but he was talking about the 100 million people elsewhere in the world. And so people did not know about the book, and therefore they had to, as we say in English, eat crow. They had to admit that they were wrong after they read the book. Just as I ate crow, admitted I was wrong when Christopher Nolan told me he wanted this much slowing of time. The spinning of space is crucial. The whirling motion of space is a big part of general relativity, and it will play an important role in a few minutes in another context. Now, in the movie, you have another very interesting phenomenon on Miller's planet. There are water waves that are 1 kilometer high. They come over, wash over the Ranger spacecraft that has landed, in which Cooper has landed on the planet. And there's 1 per hour wash over the Ranger spacecraft. And this is a film clip from the movie in which you see one of these water waves. It's the second of the 2 water waves you see in the movie.
How long for the engine's case?
A minute or 2.
Well, we don't have it. Helmet's on! Brand, co-pilot, you're up. Case, blow the cabin oxygen through the main thrusters. We're gonna spark it.
Roger that.
Locked! Depressurizing! Engines up!
That's a very impressive wave. And it's quite interesting that it doesn't break. If you've ever seen a wave on the ocean that is high, it always breaks. It always breaks due to a phenomenon called dispersion. But there are water waves like this that don't break, and they're called solitons. And they are water waves that hold together without breaking due to nonlinear effects in the same way as a black hole holds together without falling apart due to nonlinear effects. This is a soliton in water. A black hole is a soliton in warp space-time. And so it's really interesting that this movie has the two kinds of solitons, a black hole soliton of warp space-time and a soliton in water. How does this soliton generated? The fact that it's 1 hour between waves tells me just how it's generated, because I can do a little bit of mathematics with Einstein's laws. And so I'm coming to that. The key point is that Miller's planet is near the horizon, and this side of the planet is closer to the horizon than that side, so gravity is stronger on this side than on that side. The centrifugal forces of the orbital motion of the black hole of the planet around the black hole, they counterbalance gravity at the center of the planet. On this side, gravity is bigger. On that side, the centrifugal forces are bigger. So this side gets pulled down and that side gets pulled up. And for similar reasons, it turns out there's a squeezing on the sides. This is a tidal gravitational force does this, and this is the same thing as produces the tides on the Earth's oceans, that the moon creates a similar tidal gravitational force on the Earth, raises the oceans up on the side toward the moon and on the side away from the moon for precisely the same reason. And so the Miller's planet is deformed significantly. It has to be significant in order to produce waves that are this high. But the other thing that has to happen is that Miller's planet, like the moon, keeps the same face always toward the Earth, but it has not been in this orbit very long. It has to have been placed there probably by swinging around a smaller black hole fairly recently. Though fairly recently might be a long time as seen from Earth, because you remember the slowing of time on the planet. So it fairly recently is seen on the planet. So it has not yet fully settled down into that, with its one face toward the black hole. It is swinging back and forth like this due to the tidal gravitational forces, which are the restoring force that makes it swing like the Foucault pendulum that you have here in the Science Center, swinging back and forth. And when I do a calculation of the swinging period, wonderfully it is 1 hour. And so clearly what's happening is that as the planet swings back and forth, the ocean sloshes on the planet back and forth, and that sloshing is the waves that you see. It is rather like what's called a tidal bore, when the tide rises on a long river and creates a wave that travels up the river when the tide is rising. It's called a tidal bore. So this is a tidal bore, but a giant tidal bore that arises from this swinging. So this is an example of what you can do with Einstein's laws, work out details, and the details are worked out so they fit the movie, or the movie was worked out so it fits the details. I mean, Chris and I went back and forth on these things. From the equations, you can also figure out Gargantua's mass. It is the same mass as 100 million suns, which in fact is the mass of the giant black hole at the center of the galaxy Andromeda, the nearest large galaxy to our own, which is visible to the naked eye if you're near the equator or in the southern hemisphere. Gargantua's circumference then is the same as the Earth's orbit. So this is a giant black hole, as big as the Earth's orbit around the sun. It's also quite interesting to ask about how fast the planet is orbiting around the black hole. It takes about 100 minutes for the planet to go around the black hole, and the circumference of the orbit is about 1 billion kilometers. And so, as measured then from far away, looking at the planet going around and around, it's moving at about 1 billion kilometers in 100 minutes, and that turns out to be half the speed of light. So that's impressive. But now think about what happens as seen on the planet. On the planet, time is slowed down by an enormous amount. And so it is going around 1 billion kilometers in 1/10 of a second. That's 30,000 times the speed of light. That's kind of uncomfortable. So something must be wrong here. And the thing that is wrong is you have to measure the speed of the planet relative to the whirling space. Space is whirling around at almost the same speed as the planet. And when you measure it relative to the whirling space, in fact, it is moving at half the speed of light. And so everything hangs together in a beautiful way that comes from Einstein's relativity. But it emphasizes, again, the physical importance of this whirling motion of space. Now, what does a black hole look like? In order to answer this question, well, first I have to say that Christopher Nolan introduced me to a man named Paul Franklin, who was the supervisor of visual effects for this movie. And he said, I would like the two of you to work together with Paul's team at the Double Negative Company, a computer graphics company in London, work together and generate for me segments of this movie that involve black holes and wormholes and disks of hot matter around black holes, astrophysical objects that are accurate, scientifically accurate. I want the real thing, and then if it looks at all reasonable, we will use it in the movie. If it doesn't look at all reasonable, then we will have to see how we're going to compromise. And so Paul then introduced me to Eugenie von Tunzelmann, who is the leader of an artistic team who made pictures, paintings of the disk of hot gas around the black hole, and also the galaxy in which the black hole lives. And to Oliver James, who's the chief scientist at Double Negative. And so Eugenie von Tunzelmann and her team made the paintings that were to be the basis for the hot gas and the galaxy. I derived the equations for the propagation of light beams, the travel of light beams from the source of light, say the disk, to the camera around a black hole. I fed those equations to Oliver James. He wrote a sophisticated computer program to implement those equations, and then combining the paintings and the equations, he made the images you see in the movie. And Paul Franklin, the leader of this effort, got the Academy Award and the British analog, the BAFTA, for the visual effects in the film. And I was pleased and honored when at the Academy Award ceremony he thanked me for giving him the equations to produce the images in the movie. And so I think it's probably the first time a physicist has ever been thanked in an Academy Award speech. So that was one of the little pleasures of this involvement. He really should have been thanking Einstein. I've come to think of it, I think he actually did. I think he thanked Einstein for general relativity, and he thanked me and my colleagues for the physics that went into the movie. One of the things that we did was as Eugenie von Tunzelmann's team made a painting a digital painting of a large number of stars around the black hole. This is not what you see in the movie, but I'm going to, a large number of stars around the black hole. The light from this star can go to the camera down here along that path. It's the shortest path through space-time, a so-called extremal path from the star to the camera. Or it can go along this path, and there's a shadow along which the light cannot go. It could go along that path that goes down, goes around the black hole and up to the camera. And once you've seen those three paths, you can imagine that there are many more paths that it can go along. You can go around the black hole in one direction 7 times, the other direction 27 times. And so there must be an infinite number of images of every star, many images of every star, and this is called gravitational lensing. And so this is a film clip made by the team at Double Negative based on my equations of the, what you see of these stars as the camera orbits around the black hole. And if you look carefully, you're going to see down here, is it possible to turn the lights down for a moment on this? Or it's not absolutely necessary. But down here you will see suddenly where there is no stellar image, you will see a bright image appear out of nowhere and then turn into two images and they will split apart, the creation of a double image of a star. And then as one of these images of the star moves around, it will find another image of the same star and annihilate. And continually around this black hole, there are pairs of images being created and annihilating due to what is called, in technical language, the caustics of the passed light cone of the camera. And so one of the things that we did, which was a lot of fun, is we took the computer program that Oliver James wrote, and we explored this phenomenon in great detail. And I'll just let you enjoy watching this film clip. So here the camera is moving around the black hole. These are images of stars. You saw one of these phenomena. You're going to see another one about here in just a moment. There, a pair of stars appeared and split apart. And it keeps happening around here. And if you look closely, you can see annihilations of pairs. And it turns out when you look very closely that we see in this film clip, we see as many as 14 different images of the same star. Of course, there are many, many stars in here, but you see as many as 14 different images of the same star. But the number is changing as these annihilations and creations occur. Really quite interesting, but this is not what you see in the movie. This is from a technical paper that we published based on research that we did with the Double Negative computer program after the movie was finished. And so one of the wonderful things about this was we used the computer program to do physics research. What you see in the movie is this image of the black hole Gargantua. And it has become the iconic image of a black hole that astronomers now show when they talk about wanting to make pictures of black holes. They say, like the one in Interstellar. But it's not an image that hardly any of you have ever seen before the movie Interstellar. In all previous Hollywood movies, a black hole is depicted as a whirlpool going around and around, which is what it looks like from the bulk. But we are not bulk beings. We don't live in the bulk. And so that's not what it looks like to us. This is what it looks like to us, and I'm going to explain why. It has a very simple explanation, again, from general relativity. What you actually have is a disk of hot gas around the black hole, much like Saturn's rings. The IMAX camera is here slightly above the plane of this disk. And come on. Well, there we go. A light beam coming off of the back top face of the disk goes up, is bent by the warping of space and time of the black hole, and goes down to the camera. So the camera thinks that the top back face of the disk is up here. And so that is generated, that top piece of the image is generated by light beams from the back top face. Similarly, light beams from the bottom back face generate a piece of the disk that looks like it's down here, that piece of the disk. And light beams coming off the front face of the disk go directly to the camera and generate the middle part of this. And so you see then the disk in the form of something that goes all the way around, a halo, and then this crossbar, just for this very simple reason. And so that is the iconic image of a black hole from the movie. The remarkable thing, let me ask, where do disks come from? And the answer is that the black hole's tidal forces tear a star apart to produce the disk. And this is a computer simulation by two postdoctoral students, James Guiacon and Suvi Jazari. And if you look up here in the upper left corner, there's a faint blue dot, which is the black hole. There is a star up here, and the star is going to go around that black hole and be torn apart by the tidal forces of the black hole. And when it's torn apart, some of the gas will go flying out in a jet, and some of the gas will be captured to form the disk. sorry, having a little bit of, there we go. So there, it's been torn apart. The jet is formed. Some of the gas is captured up here and creating the disk. And the disk around Gargantua in the movie Interstellar was created in that kind of a manner. Now, at the center of our own galaxy, there is a big black hole. Not as big as Gargantua. It's 25 times smaller, but it's still 4 million times heavier than the mass of the sun. And these are the orbits of stars around the black hole. And you can see where the black hole is because when a star comes close to the black hole, it swings around fast, rather like a comet going around the sun. And you can watch this in a simulation that was done by Andrea Ghez at UCLA and her team based on their own observations. So up in here, you see that one go around. It whips around the black hole, which is sitting in here. So we know there's a giant black hole in there just based on the stellar orbits. By applying Kepler's laws to the stellar orbits, Andrea was able to compute the mass of this black hole and concluded it was 4 million times bigger than the mass of the sun. Now the amazing thing is that radio astronomers are going to be able to make an image with radio telescopes, an image of this black hole's shadow and its accretion disk, very much like the image in the movie Interstellar, within the next few years. This is called the Event Horizon Telescope. It combines the data from many radio telescopes around the world, and success is likely in this decade, and you can look at the details at that URL. It's just www.eventhorizontelescope.org. And the fact that we really will actually see, by combining data from radio telescopes, see a black hole shadow, even though it's so far away as the center of our galaxy, and see the disk around the black hole, that is just incredible to me, that the science is at the point where this is actually going to be observed in the next few years. Let me now talk about the interior of black holes. This involves singularities where gravity seems to become infinitely strong. Space-time is infinitely warped, and it involves the new laws of quantum gravity. The first issue is that, as I've told you, when you get down to the event horizon, time stops. And that's why gravity is infinitely strong there. And so if I ask what goes on inside a black hole, we face the issue of what can be slower than stopped time. And the answer is that time then starts to flow in a direction you would have thought was a spatial direction. It flows downward away from the horizon. Nothing can move against the flow of time. Everything is dragged forward with the flow of time. And so that's another reason nothing can get out of a black hole, is because time is flowing toward the center. That doesn't mean time travel is impossible. What it means is if you're going to ever go backward in time, you have to move always with the forward flow of time where you are. But you go out in space, always moving with the forward flow of time where you're located, step by step, and you come back before you started because time is so screwed up in the universe. So we don't know whether you can have time machines, but we know you cannot move against the local forward flow of time. And then down inside the black hole, what do you see? Well, there's an image from the movie. So I'm going to show you another film clip. In this film clip, Matthew McConaughey, playing Cooper, is riding in a small spacecraft called the Ranger spacecraft, the same spacecraft as was used to land on Miller's planet. And he is going to go through the event horizon, and he will tell you when he's going through the event horizon. And then the camera will turn around and look above him, and you're going to see what he sees looking up after he's inside the black hole. And it's really a marvelous sequence. So here it goes. I'm sorry. Here we go again.
Okay. I'm nosing down. Approaching the event horizon. Port side, dipping down beneath it to go through it.
And so you're now looking back up from inside the black hole. You see the accretion disk still. It's a little weird. The external universe is inside the accretion disk and the black hole is outside. And I'll let you figure out why that is. But that's what happens. This is from simulations, solving the equations. But it's interesting that you can see out of a black hole. Well, of course you can, because things easily fall into the black hole, including the light that brings you the image of the accretion disk. But you cannot see into the black hole. Nothing can come out, but the light easily goes in. And so this is really a very nice illustration. But inside the black hole, as seen from the bulk, things look like this. There is, down at the bottom in this diagram, and you notice that the event horizon is right there. Down at the bottom, there is a very chaotic-looking region. This is just my own artistic impression of something that is a truly chaotic oscillation of the space-time warping. And what happens as you fall into here is tidal gravitational forces stretch you in one direction, squeeze you into other directions for a moment. And then it flips over and stretches you in this direction or that direction and squeezes you into other directions. And it oscillates. The directions of stretch and squeeze, the length, durations, the length of time of the stretch and squeezes in one pattern after another, is described by what is called by mathematicians a chaotic map, a chaotic mathematical map. And it's really remarkable that you see this chaotic map coming out of Einstein's field equation, one of the many things that come out of Einstein's field equation. But the other aspect of this is that the core of this singularity, because the space-time warping becomes extremely strong, it turns out it gets controlled in the core by the new laws of quantum gravity that we don't understand. Both quantum effects, because the length scale, the scale on which this warping is occurring, becomes so short. It's governed by quantum physics, and it's governed by relativity because it's a warping of space and time. So it's governed by the combination of quantum physics and relativity. Those two sets of physical laws are logically incompatible, as we know them. And so we realize that in order to understand this, we have to have a new set of physical laws in which both relativity and quantum physics are modified in some manner so they can be made logically compatible. These are called the laws of quantum gravity. They may be some variant of string theory. They may be some variant of what's called loop quantum gravity. There are several possibilities. We don't know for sure what those laws are. I'm often asked, well, when will we know? And I look in from the outside. I don't work on these laws, even though they're the most interesting problem in physics today. I don't work on these laws because I like to have elbow room. And this is the sexiest thing going, and there are too many people working on it, and most of them are smarter than I am. And so I choose to work on other things. So I look in from the outside and ask what's going on with these laws of quantum gravity. And I can say, just looking at the progress of the last several decades, I expect these laws to be understood before I die. And I'm 75. But then I should tell you that I expect to live, I intend to live to 110. So that gives my colleagues 35 years to get these laws in hand. Okay? And I think that's a realistic estimate. Likely some variant of string theory or loop quantum gravity. They are the holy grail of theoretical physics and have been since 1960. These laws control not only singularities inside black holes, they control the birth of our universe. They control whether or not you can have time machines. Time machines, the moment you try to activate a time machine, it appears to have an explosion that destroys it. The fate of that explosion is governed by the laws of quantum gravity. So some of the biggest questions in physics today, most interesting questions, are controlled by these unknown laws. And in Interstellar, these unknown laws are very important, as I will explain. I guess I may not have it here. In Interstellar, Cooper wants to find out these laws and feed the information back to his daughter in order to save the human race. And I won't explain how this happens. I'll let you watch the movie in order to understand it. But understanding them is tremendously important in the movie, and they are referred to as the quantum data that is the holy grail of the movie, as it is for theoretical physicists today. It turns out there are two other singularities inside the black hole. The one that I talked about is so lethal that Cooper would die if he went in there to get the laws of quantum gravity. But fortunately, there are two other singularities that are a little less lethal. They're referred to by the character Romilly in the movie as gentle singularities. They have an interesting origin. Let me just talk about the outflying singularity, which is the one that Cooper hits. All the stuff that fell into the black hole over its entire past history of 1 million years, perhaps, some tiny bit of it is scattered back because it hits some piece of the space-time curvature and gets turned around and scattered back toward Cooper as he's falling in. 1 million years worth of stuff, a tiny amount scattered back. And because time is so warped in there, this 1 million years worth of stuff comes flying up at Cooper in a fraction of a second. And basically what we call a shock wave, like the shock wave of a sonic boom. And the tidal forces in that shock wave become infinite, so that you would think he would be torn apart, but they only start to become big almost at the end, and it happens so quick that there's not time for Cooper to be completely stretched and killed necessarily. What happens depends on how strong the shock is. He may be stretched by 1 meter, and he begins 2 meters tall, he's dead. But he may be stretched by 1 centimeter, and he's still alive. And so it just depends. And in the movie, he's stretched by something like 1 centimeter, and so he's still alive. But his larger spacecraft is stretched enough that it's torn apart. And if you see, there's a momentary moment in the film where you see the spacecraft torn apart just after Cooper ejects by these tidal forces. In Interstellar, as I was saying, Cooper hopes to learn the quantum gravity laws from the outflying singularity and use them to save humanity. I'm not going to tell you the details of how or what happens after this in the climax of Interstellar, but I will tell you how this climax came to be. In one of my first meetings with Christopher Nolan, he told me that he so admires Stanley Kubrick and Kubrick's movie 2001: A Space Odyssey, in large measure because of the ending of the movie, which is very mysterious and almost impossible to understand. And you go away from 2001: A Space Odyssey puzzling over this ending, which is so different from the rest of the movie and so strange, it's quite unsettling. He said to me, I want to have an equally mysterious ending, but one that is explainable. And later he said to me, you can explain it in your book about the science of Interstellar. And so I explain it in the book, but there's not time to discuss it today, and it's speculative. I want to stay away from speculation, so you have to buy the book in order to learn what the ending is about. And then you probably have to buy the Blu-ray or the DVD, and you have to go back and forth between the DVD and the book in order to understand the weird things that happen after this in the movie. But I want to move on and talk about collisions of black holes and the nonlinear dynamics of curved space-time. For just a few minutes. This is what is called numerical relativity. If I have two black holes that are about to collide in a head-on collision, you recall that space is whirling around and around near the north pole of this black hole, but the whirl of space is higher at this woman's feet than at her head, and so if she looks down from her head at what her feet are doing, they're being twisted around relative to her head in a counterclockwise manner by an amount that's proportional to how tall she is. This is called differential frame dragging, is a technical word. At the South Pole, she would be twisted around in a clockwise manner. It's like twisting a wet towel to remove water from the towel. If your left hand sees your right hand going clockwise, then your right hand will see your left hand going clockwise. So there is a handedness. It's either clockwise twist of the towel or a counterclockwise. Space is either twisting clockwise or counterclockwise. So we refer to this as that the north pole of this black hole has a counterclockwise vortex of twisting space. The south pole has a clockwise vortex of twisting space. These are structures, made out of warped space-time, attached to the black hole, and they give you a sense that there's a lot of richness to this space-time warping that we didn't know was there before. This black hole has reversed. The clockwise vortex is sticking out of the north part, and the counterclockwise vortex sticking out of the south part. And when these, and I paint on the black hole a color that indicates the color or the handedness of the vortex that sticks out of the black hole. So this is a horizon vortex, red here counterclockwise, blue on the other side clockwise. And I'm now going, and this is for the experts, this is an explanation of what these vortex lines are that guide the twisting. I'm now going to show you the beginning of a collision of these two black holes. This is the event horizon. You fall through it, you can't get out. Originally, you had a black hole that had two vortices on it, a red one and a blue one, and another one, blue and red. Now you have a single black hole with four vortices on it. Black holes don't like to have four vortices. They only want to have two. And so somehow this black hole has got to get rid of vortices. And the way it does it is quite remarkable. This is, first of all, is a blow-up of that, showing the vortex lines and the vortices sticking out. I'm going to now show you the full movie of the collision. I want you to look on the right-hand side of the collided black hole. Initially, it's blue up here. The black hole merges. What was blue is now red. And now it's blue. Now it's red. These vortices, in technical terms, they're exchanging vorticity. What was a clockwise twist of space has flipped over, has become counterclockwise, then clockwise, then counterclockwise. And what goes on with this is the following, that the vortex lines, the vortex of twisting space that's clockwise, they reach out from the blue spot on here, go around and up into the blue spot on the other side. These vortex lines have reconnected, we say. The red vortex lines come out of this red spot, go back in the other red spot onto this merged black hole. And as the black hole oscillates, every time it goes green, these vortices have to twist, but they do it by popping off of the black hole and making a ring that travels out at the speed of light. And so you get a succession of rings traveling out at the speed of light. Each ring is a vortex of twisting space, now in the form of a ring traveling out into the universe. As it travels, it creates tendexes of stretching and squeezing space, like the stretching and squeezing that goes on near a singularity. And so you have stretching space along that direction, squeezing around the little circle on the ring. And this is a complicated structure. Now it has twisting space, clockwise and counterclockwise. It has stretching space, squeezing space, all wrapped up in a ring that is traveling outward into the universe. And this, in fact, is a gravitational wave. And it travels outward to the Earth, and we try to detect it. And by looking at the shape of the wave, we try to deduce what was happening in the black hole collision that generated it. And so I'm going to end my lecture by talking for just a few minutes about searching for gravitational waves from, for example, black hole collisions. This is wonderful because we are on the threshold of a revolution in understanding our universe that will come through discovering these gravitational waves, measuring their shapes, their so-called waveforms, and then by comparing with computer simulations, deducing the weird things that go on with the warped space-time inside the source. So Einstein predicted gravitational waves in 1916, 100 years ago, next year. These are ripples in the shape of space, is one way to describe them. The other way to describe them is these are these rings of stretching and squeezing and twisting space that travel out through the universe at the speed of light. And the stretching and squeezing is the basis for the gravitational wave detectors that I'll talk about. As such a wave goes past Miller's planet, for example, it will first stretch in the vertical direction, squeeze from the sides, then stretch from the sides, squeeze vertically, and oscillate in some pattern, and that pattern is the gravitational wave shape or waveform. These collisions of black holes can also be described in terms of what is seen from the bulk. This is an artist's conception. The black holes collide and merge. And these, in fact, turn out to be the most violent events in the universe. The power output in gravitational waves is 10,000 times the luminosity of all the stars in the universe put together when two black holes collide, which is really phenomenal. And there are no electromagnetic waves emitted whatsoever, except if there's a disk of hot gas around the black holes, in which case the disk will be disturbed, and optical astronomers, radio astronomers may see waves coming from that. I'm part of a team that is doing computer simulations to compute the gravitational waveforms in order to be able to tie the observations to the theory of what goes on in the source. The waves are detected by hanging mirrors from overhead supports. The waves push these mirrors apart. They're 4 kilometers distant from each other. Push those together, then push these apart and push these together. And a technique called laser interferometry is used to monitor that stretching and squeezing. The phenomenal thing is that the motion of these mirrors relative to each other is small. It's 1/1000th the diameter of the nucleus of an atom. And I remind you, a nucleus of an atom is 100,000 times smaller than an atom. So this motion is 1/1000th of 1/100,000th of the diameter of an atom. And the superb team of experimental physicists who have built these instruments, they are able to see that today. And so this is a picture of one of these gravitational wave detectors. It's part of LIGO, the Laser Interferometer Gravitational Wave Observatory. It's in Hanford, Washington. It's a collaboration of 900 scientists at 75 institutions in 15 nations, including Poland. There are 2 such detectors operating at the present time, both in North America at these locations. There's a test bed detector that's used to develop the technology in Hanover, Germany. And then next year, one in Pisa, Italy, that is a French, Italian, Dutch collaboration will start operating. And in a few years, one under a mountain in Japan, and LIGO will put one in India if all goes well. And we need all of these detectors in order to observe simultaneously, be confident what we see is real, extract the wave shapes so that we know what the source was, and determine the direction to the source by the delay and arrival time of the waves at different locations on Earth. And so the advanced LIGO interferometers that are now operating began their first gravitational wave search 2 months ago. These are instruments that we have been planning to build for many, many years. We first proposed them back in 1989, and it's been a long haul to get here because we had to build preliminary detectors called initial detectors first and get experience with them. These detectors today have sensitivities good enough to see 2 colliding black holes 1/10 of the way to the edge of the visible universe. It's amazing how far they can see. And within 4 years, they will improve to where you can see 1/3 of the way to the edge of the observable universe. They're likely to see colliding black holes and many other sources that I've listed here, and likely to make big surprises, very unexpected things. They will truly bring, I expect, a revolution in our understanding of the universe. And that revolution will come sometime between today and 4 years from now. I'm going to skip over this. This is just a technical description of the noise in the source, and just conclude by saying that general relativity in these first 100 years, the small number of things that I've described to you, the prospects for gravitational wave detection, the prospects to see with radio telescopes, the black hole at the center of our galaxy and its accretion disk, the changes from 100 years ago when Einstein formulated his general theory of relativity, they are truly amazing. Thank you.